demonstrated functions, function operations, and function composition in other videos. And in this video, I want to focus on one particular use of a function on the synthesizer, amplitude modulation. Amplitude modulation is what is behind transmission of information in AM radio. In simple terms, there are two waves, the carrier wave and the modulating wave. To demonstrate this with the synthesizer, I will have a sine wave on oscillator 1 be the carrier and another sine wave on oscillator 2 be the modulator. On the spectrum analyzer, you can see the first sine wave has a frequency of 220 Hz. Notice it's between 100 and 500. And when I bring up the second sine wave, it will have a frequency of 880 Hz. Notice it's just below 1K or 1000. The vertical bars for both reach the same point. This relates to the amplitude. Quite simply, amplitude is related to volume output by means of voltage. What I will do now is put the first sine wave into a voltage-controlled amplifier, or VCA. There is a knob on the VCA that allows me to turn the volume up or down. But since it is voltage-controlled, I can have that knob turning controlled by other parts of the synthesizer. I'm going to have the second sine wave do this controlling. However, because the frequency is so high, we won't hear the volume going up or down, but something more interesting is going to happen. Let's inspect the output of the VCA in the spectrum analyzer. Here's our original 220 Hz sine wave. And now I've brought in the 880 Hz sine wave to modulate the VCA. Notice that the original frequency bar is still there for 220 Hz, but two additional bars showed up, each at different frequencies and at lower amplitudes than the original. So the final output has additional frequencies added. The reason behind this has to do with trigonometric identities. For the first sine wave, we'll use the equation y1 equal a1 sine of 2 pi times f1t, where f1 represents the frequency and a1 represents the amplitude, which is really just the highest y value or volume that can be reached. Similarly, y2 equal a2 sine of 2 pi f2t is the equation for the second sine wave. When we use the second sine wave as a modulator, we are adding the changing y values or voltages to the amplitude of the first sine wave. The result becomes parentheses a1 plus y2 times sine 2 pi f1t, which breaks up to a1 sine times 2 pi f1t plus y2 sine of 2 pi f1t, which further breaks up because we can replace what y2 is, and we get a1 sine of 2 pi f1t plus a2 sine of 2 pi f2t times sine of 2 pi f1t. Notice that the first part of the result is our original first sine wave, the carrier. This reminds us of how we saw the original frequency as a high vertical bar in the output. For the second part, we'll use a trig identity. What I'm using here is the product to sum formula. And from that, what we get is that the second part of the output, a2 sine of 2 pi f2t times sine of 2 pi f1t, is equal to 1/2 a2 times the quantity cosine of 2 pi times f1 minus f2t minus cosine of 2 pi times f1 plus f2t. What we have done is rewrite the product of two sine waves as the difference of two cosine waves. However, in real sound, we move away from some of the strict general nature of the theory. From learning about the sine and cosine graphs, we know that they have the same shape and are really just a phase shift from each other. Furthermore, when we negate a sine or cosine wave, it still has the same shape. It has just been flipped vertically over the horizontal axis. What this all means is that cosine of 2 pi times f1 minus f2t sounds the same as sine of 2 pi times f1 minus f2t, and negative cosine of 2 pi times f1 plus f2t sounds the same as sine of 2 pi times f1 plus f2t. The only important thing we need to take away from the result is the following. The first cosine wave has a frequency that is the difference of the original two frequencies, and the second cosine wave has a frequency that is the sum of the original two. If we use our original frequencies, 220 and 880 Hz, this means the result would have the original wave of 220 Hz present along with two others at 660 and 1100 Hz. If we look at the spectrum analyzer, we can see that there are two lower vertical bars, one of them between 500 and 1000, and the other one is just to the right of 1000. So the product to sum identity was very useful to help us understand why we were seeing and hearing what we did with this amplitude modulation. To finish, let's get a better understanding of how the volume of the amplifier is truly going up and down. We can't hear this when the modulator has a high frequency, but if we lower the frequency, then we can hear it. So here I've brought back our original 220 Hz sine wave, and now the modulator will be another sine wave that has a very low frequency. And if we look at the oscilloscope, we can notice that the amplitude is increasing and decreasing, which relates to the volume going up and down due to this modulator. There is a popular use of amplitude modulation in recorded music. It is an effect called tremolo. Here's an example.